And welcome back to a video series on MAT 1033 Intermediate Algebra. My name is Sean Perry. This is video number 41 in the series, Factoring General Trinomials. So as opposed to a monic trinomial, a general trinomial may have a leading coefficient other than 1. Let's start with an already factored example. Let's take 2x plus 1 and FOIL it with 3x minus 4. So keeping track of my terms here, I have 2x times 3x, that's 2 times 3, x squared. I have 2x times minus 4, that gives me 2 times minus 4x. I have 1 times 3x, that gives me 1 times 3x. And I have 1 times minus 4, which gives me a minus 4 down here. But you probably noticed that I haven't reduced it immediately. I want you to see how these four numbers, 2, 1, 3, and minus 4, sort of contribute to each term. The 2 and the 3 contribute to the first term. The 1 and the minus 4 contribute to the last. But the middle term has a little bit of all four of them sort of mixed in to this minus 5. So that sort of shows a little bit of the problem, but let's at least proceed naively. Let's try to come up with some kind of general formula or something like that by looking at things the way we did last time. Looking at a general factored version and seeing what the terms look like. This is what gave us our strategy before. Maybe it'll work this time. So a general linear term will have the form something times x plus something. If I multiply two general linear terms, we start to see a little bit of the problem. We wind up with two terms multiplying to give the leading coefficient, two terms multiplying to give the last, and then a mixture of all four of those terms giving the middle coefficient. Yeah, so that's cool and all, but is it really useful? I mean, can we factor thinking about it? Well, maybe someone out there can, but I don't know if I can do that. Like, you'd have to ask a very strange series of questions to be able to approach this like the last one. What four numbers, two of which multiply to be the first, two of which multiply to be the last, and then this pairwise product and sum thing gives me the middle term? Okay, so that's maybe a little too complicated to be useful. But let's go back a step and try to use the same algorithm as we did before to factor, and make maybe a slight modification along the way so that we don't have to deal with this whole confusing question. And right, that question, as I just said, is what are two factors of the first number and two factors of the last number that can multiply pairwise then sum to get the middle term? Yeah, way too confusing. We're not going to do that. That's silly. So let's start with this polynomial. And this is a good place to start because we already know what its factors are. This is what we expanded to get our first example. So we have 6x squared minus 5x minus 4. So I should note that there are many different strategies for doing polynomials that look like this, for factoring general trinomials. We're going to use one that's called the AC method. It's called this because if we call the first term A as its coefficient, then B for the middle term's coefficient, then C for the last term's coefficient, we're going to focus on A and C. And their product is going to key us into what factors we're looking for. To begin with, set up your parentheses like this. Leave a little additional space out front and a little additional space in between each one of the x's, but start to set it up the same way we did for monic trinomials. Then you're going to want to fix your signs. Drop this negative sign down just like before. What times a negative will give me this negative when I FOIL? Well, we're going to need a positive. And now here's where it starts to get a little crazy. Instead of trying to fill up all four of these spaces, I'm going to fill up the first one with 2 copies of 6. Wait, what? Yeah, okay, if we left it like that, it would certainly be wrong. So what we're going to do instead is fix it by putting a 1 over 6 out front. And this should all be seeming a little bit zany right now. Why on earth would we do that? This definitely merits some comment. But look what we've done. We now only have 2 empty spaces. And really, nothing is wrong yet. If I look at the first term, 6x times 6x, that's 36x squared. But if I take a sixth of that, it's still 6x squared, which is the term that we need. So there isn't a mistake. We've made no mistakes, and yet only 2 blanks remain. But there was a cost to doing this. What we had to do for this little bit of judo to work is we had to multiply, essentially, by an extra 6 inside the parentheses. You would agree there is an extra 6 inside this parentheses. And effectively what we've done is multiplied by an extra 6 within the parentheses. Now, what that means is instead of just looking at the factors of the last term, which was 4, we have to look at factors of 6 times 4 because we've multiplied by an extra 6. Now, that's why this is called the AC method, because we're looking at the factors of A times C. All right, so let's jump back into solving this problem. We look at factors of A times C. What is that? Well, 6 times 4 is 24. And since we're looking at different signs here, we need a difference of factors of 24 that give us the middle term of 5. Well, looking down my list, that's 8 and 3. And now, just like before, I can pop that 8 into the first slot, the bigger one goes first, and then put the 3 in the next one. And then all we have to do to get the right answer out of this is sort of take out the extra factor of 6 that we put in before. So what I can do is divide the greatest common factor out of each one of these parentheses. Of 6 and 8, the greatest common factor is 2, and of 6 and 3, the greatest common factor is 3. So I can pull out a 2 from this one, a 3 from this one, and hey, that's 6. So when I take a sixth of 2 times 3, I just get 1, and everything disappears. And all I'm left with is the first terms that we had in the first place, 2x plus 1 and 3x minus 4. We factored that polynomial. Essentially, what this method does is it puts an extra a inside of the factors, and this allows us to focus on just the last 2 slots rather than focusing on all 4. The cost of this method is that we wind up having to factor a larger number, a times c, and we have to reduce things at the end, but that's it. This may seem like a lot of steps at first, but once you practice the method a little bit, I'm sure you can get it. And then once you get it, the process really doesn't take too long, even if the factors get a little large. I'll prove this in the praxis below, but for now, let's do some critical notes. Copy this, show it to me later. This is the AC method for factoring general trinomials. Scroll down to get the important stuff in frame here. And what do? Let's say I wanted to factor something like 8x squared plus 22x plus 15. First, I need to identify A and C. That's what we're going to pull out. But we can also set up our parentheses, leaving these spaces, fix our signs, a plus and another plus. We put A's in each of the first 2 slots, that's 8 in this case, and a 1 over that out front. Just do this all at once. Set the whole thing up just like this. And now look at A times C. That's 8 times 15. That's 120, which has the following list of factors. What are we looking for? We're looking for 22. It's same sign sum, so we're looking for a sum of 22, and we find that with 12 and 10. Putting my 12 here and my 10 here, I could factor out a 4 from this one and a 2 from this one. Notice that's just 8, so when I pull those out, they cancel, and we're done. That's the end. That's the factored version of this. 8x squared plus 22x plus 15 factors as 2x plus 3 times 4x plus 5. So this 1 over a term that I put up front, this is just a device that makes sure each line is really equal to the one I had before. I like to write a chain of equal signs, and I like them to really be equal to the thing that came before it. The 1 over a always cancels, and I find that cancellation very satisfying. You may have seen other AC method versions that just skip this step of balancing out the a term, but I think you should keep it in. And because we want all of our lines of mathematics that we write to be both true and justified. Sometimes people don't say why we're timesing a by c in the AC method. They just say, oh yeah, just do it, it works. I hate that. I really don't like that. What we're doing is pretty simple. We are putting an extra a multiplied inside, and that's letting us really easily and quickly fill in the first 2 slots. There's an extra times a in there, so why shouldn't there be a divided by a out front? If I times by a and divide by a, nothing really bad has happened, so it should be fine for me to put an extra a multiplied inside if I put a 1 over a out front. And that extra a inside means we have to look at a times c. That's why it's working. That's why the method is going to be giving us the correct answer, and we should keep track of that. It should be justified and it should be true. So all of this becomes much more familiar with practice. Let's practice. So you can either pause the video if you like, try this one before we get to our praxis, is fine with me, but I'll also work this out. Let's say we wanted to factor 10x squared minus 19x plus 6. The first thing I would do is set up my parentheses, leaving these little spaces when I deal with non-ones up front here. Then I would fill in my signs, same as before. Drop the minus sign down. What do I need to multiply by this minus sign to give me this positive in the end? I need another minus. Then I'd put 10 in each position, a 1 over 10 out front, and then I'd start to look at my factors of a times c. A times c is 10 times 6, that's 60, whose factors are 60 and 1, 30 and 2, 20 and 3, 15 and 4. When can I stop? I can stop when I have a same sign sum of 19, and that comes with 15 and 4. Now we reduce. We divide out the greatest common factor, which is 5 from this one. We get 2x minus 3. We divide the greatest common factor out of this one, which is 2, and we get 5x minus 2. And this is going to cancel with the 1/10. 5 times 2 is 10, times 1/10 is 1, and we have our remaining factors. So this is the factored form. We could check, if we wanted to, 5x times 2x, that's 10x squared, minus 3 times 5x, that's 15x, minus 2 times 2x, that's minus 4x, and 15x plus 4x is 19x. Minus 3 times minus 2 is positive 6. The checking is complete. This really isn't so bad. The cost was that sometimes we have to factor this bigger number, a times c. And that number, it could be large, right? It could be in the hundreds even. And in that case, I really like to bust out an old friend from grade school that you might not have used in a while, but I think is kind of useful here. And that friend is a factor tree. Let's say I had to factor 360. Maybe that was my last term. Man, that's a big thing with a lot of factors. How can I systematically go through all of them? Well, I'll show you how I made this list, but first let's talk about this tree. You pick any two factors you can see, and since it's got a 0 on the end, I can see there's a 10 here. Now I'm already dealing with smaller numbers, 36 and 10. Then we break each one of these up, continuing to do so until we wind up with just prime numbers. Once we do that, all the factors of 360 are laid bare. And let me show you how you can go through them to get this list of factors I've put to the side. Obviously, 360 is 360 times 1. And maybe you even think it's obvious that 2 times 180 is 360, but let's see how we might see it. We have 2, and then I have all this other stuff. I've got 2 times 3 is 6, times 3 is 18, times 2 is 36. Oh, that's tricky. Why don't we just do 5 times 2 is 10, and 3 times 3 is 9, times 2 is 18. So 10 times 18, that's 180. What about this one? Well, we've got a 3, and then I have 2 times 5 is 10, times 3 is 30, times 4 is 120. And we keep on doing this. We cover up the ones which we are using. Let's say we wanted this one. Well, cover up these two. How many are left? That's 4. Then there's 3 times 3 times 2 times 5. 2 times 5 is 10. 3 times 3 is 9. So this is 90. And so on. We could just keep doing this. And what's nice about this is when you come to something like, is there any 7s? Well, no, 7 is prime and it doesn't appear in this list. So there's no 7s. What about 8s? I skipped 6, but let's just say, what about 8s? Well, here's 2 times 2 times 2. That's 8. And so covering those up and just looking at the ones that remain, that's 3 times 3, which is 9, times 5 is 45. So 8 times 45 is 360. Now we could do this through the whole factor tree. I'll just mention a couple nice features. For example, we can see there's no 11s. We can see that there's no 13s or 14s because there'd have to be a 7. There's no 16s because there'd have to be 4 2s for there to be a single 16. And we can get some of these harder factors by doing this covering method. So let me show you one more. What about the 15? Well, 15 is 5 times 3. What's left? 2 times 3 times 2 times 2. That's 6 times 4. That's 24. Done. And so using this method, you can come up with a list of factors pretty quickly. And so even if the number gets large, you can wind up with producing the factor list that you need without too much trouble. I'm not going to say this is really, really easy, but it's certainly not so bad. Okay, these. Alrighty, that brings us to the praxis exercises for the day. Pause the video at this time and try to factor these polynomials. All right, let's take a look at how you did. So just like the last video, I'll go through each one of these sort of in line here to show you how I would approach it. First of all, I would set up my parentheses. Once you get decent at this, you can really kind of predict how that's going to look. I'm going to need a plus and a plus. I'm going to need 1 over 6s and 6s in each position here. And then we take a look at 6 times 20, which is 120. And we want to go through that and make a factor list. So what are we looking for? We're looking for a sum of factors, same sign sum, that give me 23. Here I have 2 and 60 and 3 and 40 and 4 and 30 and 5. Yes, even 5. 5 goes into, well, maybe this is a great time for a factor tree, right? This is 12 and 10. This is 5 and 2. This is 4 and 3. This is 2 and 2. And so I have 5, and then the rest of it is 2 times 2 times 2 times 3. That's 24. 8 times 3. And let's keep going. What about 6? Yep, 3 and 2. And then I have 2 times 2 times 5 left over. That gives me 20. Could have seen that. Well, we have to keep going. What about 8? Well, there's no 7s, right? So what about 8? Is there an 8? Yes, there's 3 2s. 2 times 2 times 2, that's 8. And then 5 times 3, that's 15. Hey, wait a minute, that's 23. So we found our numbers. We put them in, 15, 8, and then I reduce. I divide out a 3 from this one. That's 2x plus 5. I divide out a 2 from this one. That's going to be 3x plus 4. And the 2 and the 3 cancel with the 1/6, and we're done. That's it. That didn't take long. That took a couple minutes. So let's keep working on these, and I'll show you some more examples or confirm, your examples that you've hopefully done. You really pause the video and try these. By the way, I know that you can just stop the video and wait for me to do it, but you'll learn a lot more if you really try them before I show them to you and see where you get stuck, right? You want to know where you get stuck so that you can get unstuck specifically, right? And not just kind of look at the final example and stay stuck. That's not as helpful. Okay, so what do I do here? I set up my parens. I'm going to need an x and an x. I'm going to need a plus, and plus times a minus gives me a minus. I need 1 over 7 and 7s in each one of these positions to put the a's where I need them to go. And now we look at a times c. A times c is 7 times 15, which is 70 plus 35, so this is 105. And so if we wanted to break this down, right, we could take 105 and break it down, hey, into 7 and 15, why not? And this is 3 and 5. And so we now see there's a very limited list of factors here for 105. We don't have any 2s. We have a 3, though. And that 3 is going to be times by 7 and 5. That's 35. We've got a 5. And that's going to be times 7 and 3, which is 21. And actually, we have a 7, but we could stop here, right? 7, 3 times 5, right? That's 15. But we can stop because what we were looking for, this is difference signs difference, and that's right here. We have a difference of 21 and 5 gives me 16, the middle term. So we put our 21 first, we put our 5 second, and we reduce. Notice I can't take anything out of this one, but I can take a 7 out of both of these terms. That's going to give me x plus 3, and this is going to stay 7x minus 5. You can FOIL this out, check that we get the above, but that's going to be our answer. Let's keep going. Again, we have our setup step. I gave a suggested order for these, but once you get sort of used to the pattern, you can do it however you like. A minus times what will give me a minus? A minus times a plus will give me a minus. 8 times 7 is 56. 56 and 1, well, even if you don't know your times tables up to 56, right, we could always make a factor tree. We could say 56, which was 8 times 7, and that 8 turns into 3 2s. And so this is going to be 2 times 4 times 7, that's 28. Are there any 3s? No. Are there any 4s? Yes, there's 2 2s. And then the rest is 2 times 7, which is 14. When can we stop? When we have a difference, because this is different signs difference, of 10. And there it is, 14 and 4. So we put a 14 here and a 4 right here, and then we reduce. I can pull a 2 out of this one, which is going to give me 4x minus 7, and I can pull a 4 out of this one, which is going to give me 2x plus 1. All right, let's keep on going. This one will probably have quite a large thing for us to factor, but let's just do it. So we're going to need 1 over 12, 12x minus, then 12x minus times what gives me a plus? Another minus. And now we need 12 times 40, which is going to be 4 times 12, that's 48. So this is going to be 480, pretty big number there. Let's take a look. 480 breaks down by 12 and 40, like we saw. And then this is going to be 4 and 3, and this is going to be 2 and 2. And our 40 is another 4 and 10, and this is going to be another 2, 2, 2, and 5. Okay, so we've got 2 times 2 times 2 times 2 times 2 times 3 times 5, and that's 480. Wow, big old tree. Okay, but what are we looking for? We're looking for factors that add up, same sign sum, two minuses, sum up to be 47. Okay, so do I really need to start all the way at the beginning here and move up? No, we don't have to list them all. We're looking for 47, and that's a lot smaller than 481 here. We're going to have to go pretty far down the list. Let's just see if, I don't know, let's pick one. How about 8? Got any 8s? Sure we do. This is 8 right here. 2 times 2 times 2. What do I have left? 5 times 3, which is 15. 15 times 4, which is 60. And that makes sense, right? 8 times 6 is 48, so 8 times 60 is 480. That's 68, that's not 47 yet. We must go further, right? What about 10? I mean, yes, there's a 9. Yes, there's a 9. We could even see 10 pretty easily. 10 times 48, which is a sum of 58. Still not far enough. Let's keep going. What about 16? Yes, there's 2 times 2 times 2 times 2, 4 2s. What's left? 15 times 2, which is 30. Wait a minute, that's 46. We went too far. Let's step back by 1. What about 15? Is there any 15s? Yes, there's a 15. We've got a 5 and a 3. And what's left? 2 times 2 times 2 times 2 times 2, that's 32. And hey, 15 plus 32, that's indeed 47. So we take our bigger number, 32, we put it here. We take 15, we put it here. And then we reduce. So what can I pull out of this one? I can pull a 4. That's going to be 3x minus 8. And what can I pull out of this one? I can pull out a 3. That's going to be 4x minus 5. And we're done. So what's the takeaway here? You really don't need the full list of factors. That's not necessary. You can sort of jump around. As one number gets bigger, you might have noticed that the sum is getting smaller. 481 and then down to 68, and we're trying to get closer to 47. If it's a long list, don't waste your time looking at the whole list. Jump to the middle and see if you can find your number there. Here's going to be a good example of that. So let's take a look at this one. We're going to need 1 over 9, 9x minus 9x. A minus times a minus will give me that plus. And then we need 9 times 64. Okay, well, 9 times 64 is 9 times 4, that's 36. 9 times 6, that's 54, plus 3 is 57. So 576. But do we really care? No, we're going to break this down. This is going to be 64, and this is going to be 9. This is going to be, well, 8 and 8, which is going to be really 6 2s. And this is going to be 3 and 3. Should we start with our 576 times 1? No, not really. We should jump way down the list because look, we're going to need to get to 48. Okay, well, let's try, I don't know, how about splitting it in half? We've got all of these pairs, right? We've got 3 and 3. We've got 3 2s and 3 2s. What about 3 times 8? How about 24? Well, yeah, we also know the other one is 3 times 8, that's 24. And wouldn't you know it, 24 times 24, that's as low as we can go, actually. Everything else is going to repeat factors and get larger in its sum, and that is 48. So we really just need a 24 and another 24? 24s in both slots? Yes, that's right. That's right. Now, this might have been a long process if we'd filled this all in, but I encourage you to sort of skip around, right? You're trying to get down to a sum of 48. So you might as well, skip these first terms that you know are going to be way too big. What else do we got? Well, we can also reduce. We divide 3 from each term, right? 3 out of this one will give me 3x minus 8. And there's going to be 2 of these, so we might as well just write it as a square. Now, you might have noticed 3 is the square root of 9, and 8 is the square root of 64. In the next video, we will learn about this special pattern that we can use to sort of simplify problems that look like this, where the first and last one is a square. If the middle term is twice their product of the square roots, then we can just jump straight down to this line if we know the formula. So we'll look at that later. But for right now, let's look at another special case. Perhaps if you remember from the last video, this should really be thought of as 9x plus 0, 9x squared plus 0x minus 64, right? We're looking for a 1 over 9 here, a 9x plus, and a 9x minus to give me a minus here. And then again, the factors of 64, but remember, we're looking for a 0 difference, right? The difference, different signs difference, between these two terms has to be 0, which means they have to match, which we saw before. That's what happened with 24. And we also saw what happened if I pulled out a 3, right? We're going to wind up with 3x minus 8 here. And over here, oh, plus 8. And over here, we'll wind up with 3x minus 8. And yeah, this is, again, the square root of this term, and this one's the square root of this term, and we just have a difference of signs. We will, again, in the next video, when we look at special products, we're going to look at a formula for recognizing this special case and avoiding having to do this whole general trinomial factoring when it comes to the difference of two squares. So before we close this video, I'd like to give you some additional tips and tricks when dealing with polynomials. The first thing is that you should always try to simplify first before you try to factor, and that means dividing out the greatest common factor. This was the first factoring method that we learned, and it should be your first thing you try when you're trying to factor a polynomial. For example, say you were asked to factor this cubic polynomial. Now, you might not know how to approach a cubic with only 3 terms that doesn't have factoring by grouping already set up for you, but you should notice that every single one of these coefficients has a 2, and every single one of these terms has an x. That means we can factor out 2x from everything. And once we do that, the other polynomial that remains, x squared minus 4x plus 4, is actually attackable. That we could set up our parentheses, factor it out as a perfect square, and so we get something nicely factored. We just had to take out the greatest common factor first. So if you notice that you have a polynomial of degree more than 2, you have some kind of cubic or quartic or higher, the first thing you should try is factoring out the GCF. If it's a cubic and it has 4 terms, you can try factoring by grouping, but only if you have all 4 terms. In general, you want to try to factor out the greatest common factor first, bottom line. Here's another example. Notice that each one of these has at least an x squared that can be divided out of each one. So dividing out x squared leaves me a polynomial that remains, which I can factor. Once we take out this x squared, we just have a quadratic here. And that factors in the same way that we saw in the last video. This kind of factoring out procedure is used to deal with a lot of things. For example, we can use it to deal with a negative leading term. I wouldn't try to deal with a negative in place like this and figure out, some sign rules for my leading term. What I would do is I would divide a negative out of everything. And that changes my leading term to positive and allows me to proceed exactly as we've been doing. So if you see a negative leading term, it might help you out to just factor out a negative sign, change everybody's sign, and continue from there. We could even kind of use this to deal with fraction coefficients. We've really only looked at whole number coefficients, but fractions are actually just as easy to deal with as long as we can manipulate the greatest common divisor. For example, here I have a polynomial with fraction coefficients, and it looks like it's going to be much trickier to think about. But we notice that we have a half, a third, and a sixth. That has a greatest common divisor of 6. And if I factor that out, or if you prefer, if you don't want to see this as dividing each one of these terms by a 6th, you could also say, look, I'm going to multiply that thing by 1/6 times a 6th. And 1/6 times a 6 is just 1. So this is a legal move. But what happens if I distribute the greatest common divisor? We learned in our fraction video that the greatest common divisor is the fraction killer. It deletes or turns into an integer all of the fractions. So when I distribute this to each term, we're going to find whole numbers in its place. And once I have whole number coefficients, I can proceed exactly the same way we have in this video. We take out 1 over a, we put a in both positions, we multiply a by c, and we say what are the factors of that, which give me a different signs difference of the middle term. It's 3 and 1. And finally, removing that common factor of 3, we get our final form. Here we have a factored version of this polynomial. Now, if you wanted it back to expanded, you could FOIL this out and distribute the 1/6. But if all you want is it factored, here we can see the factors laid bare for us right here. We have 3x plus 1, x minus 1, and a coefficient, a leading coefficient of 1/6. Now, it needs to be said that not all polynomials factor. You can do this procedure. You can set up your parentheses. You can look for the factors at sum or difference of the middle term, and they're just not there. There are no factors that do it. What happens then? Well, nothing. You can't factor it. Just like there are many numbers that don't break down into anything else other than themselves times 1, we call those the prime numbers, a polynomial might not factor into smaller polynomials, and we call these prime polynomials. For example, consider x squared plus 3x plus 5. I could set up my parentheses, I could drop my signs in place, I could say what are factors of 5 that sum to be 3, and then we see there are none. So that's the end. It doesn't do this. We have to stop and say, well, this is as far as we can go. We'll see what to do to find the zeros of this kind of polynomial or what are its roots in a later video. But for right now, we should note that the prime numbers are kind of special in the sense that prime numbers, we see fewer and fewer of them in density as we go up in our numbers, right? The bigger our numbers become, the fewer there are primes. If you're interested in that, look up the sieve of Aristophanes. Now, the prime polynomials, on the other hand, are common. In fact, if you just randomly pick integer coefficients, say less than 10 or less than 100, you grab polynomials with coefficients randomly chosen, most of them are going to be prime. Most of them are simply not going to factor. So it's actually special polynomials that do factor. And so the questions that we ask you about, hey, factor this polynomial for me, we have to sort of think about those beforehand. You can't just randomly pick numbers and have it work. All right, that does it for this video. Thank you very much for your patience. Have a great day and good luck with your studies. I'll see you in the next one.